Now let's load the raw data, and let's inspect the pipeline. There's nothing in the filter pipeline here except the probe. And as we noticed before, if we load a scalp from the original workspace and look at it in Visualizer, scalp and sensors, the sensors some of them are underneath the scalp. They just need to be projected to the scalp. So what we did was, I think you already did this, but say edit, fit electrodes to scalp. Now if we go back and look at it again, now our electrodes are on the scalp. And now, just so you know, that hasn't changed the CLP file here, but the probe that's in the ppm here has been changed. So therefore, just so you know, if we unload this one and reload it, let's say we come back tomorrow and reload it, you don't have to fit the probe to scalp anymore, because the changes, see, it's already fit there. That's because the changes were made to this probe in the ppm, and EMSE routinely saves this filter pipeline. So that was preliminary. Now the other thing I notice here is that we have a DC recording. There are DC offsets. So what I almost always do from scratch when starting with one of these is I add a polynomiality trend. This third order, it's a very gentle high-pass filter. It will remove constant, linear, quadratic, and cubic trends throughout the whole recording. So let's say OK there. Okay, so now we can see all the channels. There's the second 32, the first 32, and it so happens that the channel 65 is present here, but it's set to pass through. So it won't be used for source estimation here. If we want to use it for source estimation, we'll need to provide a location for it in the probe. But as it is, we can see it, but we won't be using it for source estimation. Okay, now let me say a word about an initial word about the reference, and then we'll come back to this later, because I think this turns out to be an important issue for cerebellar source estimation. So right now what reference we have in the data is whatever reference was used during the acquisition, during the recording. And I don't know what that is. But I do know that I've played with this data, and often we would start here when we would set a common average reference. But I've found that doesn't appear to be optimal for cerebellar source estimation. So I'll show you that later in this recording. So right now I'm going to leave it implicit. And we'll have to return to that issue later as to what the reference actually is. Right now I'm going to leave it implicit. But I do want to note, it looks like Dr. Suzuki may be interested from prior research reports in focusing on 8 to 14 hertz. So I'm going to add a digital AR filter here. This part I'm adding is just annotation for future reference. It doesn't affect the actual filter. And I think I will actually include channel 65, so we'll filter it in the same way even though it's pass-through channel. We'll set this to band pass. We want 14 to be the high cutoff, and 8 to be the low cutoff. Let's look at the transfer function. Okay, this goes all the way to 250 hertz, so you can, let's change this, say this, so it just goes to 20 hertz, and say update here. Now we can see it better. And we might want to slightly increase the order of the filter here. For example, from 12 dB per octave to make it a little bit steeper, so say 18. Let's say 20 hertz again. Update. See, that just makes it flatter up here, make it a bit steeper here on the roll off. So let's say OK. OK. Now we've got first 32 channels, second 30. We see oscillations occurring in the 8 to 14 hertz range, and we're still in the time domain. And now let me make an average on these DINs, DIN 1s. So let's select that. I'm going to suggest that we try negative 0.3 to positive 0.3. The reason being that these are motor movements, I gather, and therefore the brain activity preceding the movement is significant. We can't really consider it to be baseline like we could with the stimulus. And we might expect the pre-motor activity to be at least as interesting as the post-motor activity, if not more. So I'm going to, you can make this what you like, but I'm going to go from negative 0.3 to positive 0.3. I'll leave this option here to so that when we do the analysis, we'll be making larger windows, and then we'll trim it down here. That's just to accommodate the filter that we have in the pipeline here. So we'll say next. Here we could do some artifact rejection. Probably not on channel 65. At the very least, this may not reject anything, but at the very least we might say from minus 100 e to the minus 6, minus 100 microvolts to 100 e to the minus 6. E to the minus 6 is for microvolts. Since we filtered the data, this may not reject anything, but we'll see what happens. If something's bigger than that, we probably would definitely want to reject it. So let's see what happens. No conditionals. And once again, I would not baseline correct this one because of the reason we just said. Pre-motor activity is significant. It's not really baseline. So we'll say finish. See if anything gets rejected. Nothing got rejected with that criterion, so we got all 100 back, and I'll say OK. And now I'm going to add a new folder called map, my initials, just so you'll know what things I added. And let's call it DIN 1. DIN 1, and let's say 8 to 14 hertz. And let me say implicit. Now we'll add a common average reference to this later, but I just want to note that so far we haven't added an explicit reference to the data yet. So here we are. let's look at it in superimposed mode, and we can see oscillations here in the 1814 hertz range prior to the event, the DIN1 event. Following the DIN1 event, there's still something here, but then it gets smaller. So indeed, pre-event activity does look to be interesting, significant here. We could map it. So here's kind of a maximum at, this looks like 87 milliseconds pre-event. Let's just take a look at it. It looks like. Okay, hard to tell from that exactly what it might be. We have our scalp loaded, so let's look at it here. Let's look at it with contours over the map. Okay, now we can see just a little tiny hint from the contours. We can see there is a hint here because we can see these contours. There's a hint of something cerebellar. But let's see what the source estimation shows. Okay, so now let me go to source. Let's do tomographic estimation. And let's use ordinary Loreta. This is what I call Loreta Classic. EMSE Loreta is a different flavor of inverse, and it's really more related to a scanning beamformer than the original Loreta, in spite of the name. A key point here is that in the lattice, we need to go down deeper. So the z-axis is are the axial slices that go from top to bottom, or from bottom to top. So I'm going to make this negative so that it's going to start at 2 centimeters. These are in meters. So it's going to start at 2 centimeters below. It'll actually start 4 centimeters lower than the default values. So that's going to be important to see the cerebellum. And the forward method, let's start simple. Let's just do the 3-shell sphere because it'll compute faster, and we can always come back later and refine things with finite element. Okay, so I'll say OK here. Forward matrix calculates quickly with the 3-shell sphere. It's important, I'll note while this is calculating that for the forward and inverse, that they will not depend on the IIR filter. This won't depend here with this method. It won't depend on the fact that we chose 8 to 14 hertz. But it's spatial, so it does depend on the reference. So I'm going to call this one Loreta. I'll say CB is a typical abbreviation for cerebellum, and let's say implicit ref, because the inverse operator will depend on the reference that was in place at the time we made the operator. So let's save that. Let me add it to the workspace. And here we are. Now already we can see something here that looks promising, possibly cerebellum. This, by the way, is the average over this entire time interval. But already we can see something here that looks like it might be cerebellum. Let's select. Oh, actually, it might be this selection at this time range because I already had selected that. Let's go to display, refresh. Yes, and that didn't change. So if I do display, refresh here, you should notice a subtle change or something. Yeah, it changed. We still see what apparently is cerebellum. I'll look at that in MR Viewer to make sure. But so what we really want to do is save this as map data. What map data means, we're going to save all of these maps for the whole time period. So up here, I'm going to click anywhere up in the time series. I'm going to do Control A to select everything from -300 to +300 milliseconds. Now I'm going to do File, Save As, and save it as map data. The map data means it's going to save the entire, all the maps for the whole, all those latencies. So we're going to call this, let's call this Loreta CB implicit. I should probably say DIN1 because this is now based on the data. Loreta CB, that's just indicating that we made the lattice go down deeper. Implicit ref, and now this since this is based on the data and the data have been filtered, it will depend on the filter at this point. So let's say 8 to 14 hertz. So we saved the map data. Do you want to add it? Yes. Okay, so I just added that and it shows up here in the workspace. Notice underneath it there's something. I'll show you that. So let's go over to the MR Viewer side. So I haven't done anything yet in MR Viewer. Oh, let's do, before I go to MR Viewer, see this workspace is asterisk needs to be saved. So I'll do File, Save. So now now when I go on the MR View side, I'm going to load that same workspace that I just saved. So I'll say Open. Let's see, I may need to navigate there. Yeah, I'm in the wrong place, but I'll get there shortly. We have, this is where it is. This is where we are. And that's the one I just saved it. So now we're in MR Viewer. Let me move this over here just a little bit, this workspace. And now we're going to load the VMI data. So there's the VMI data. Let's oh, the probe showing here, by the way, is this one, which I don't believe I saved. But it's not going to be a problem on the MR View side because we're going to view the map that was created from EMSE source estimator. So it's not going to be recalculated here. However, we could have resaved the probe at the time that we fit the scalp. Or we could also fit the scalp here if we want. I could say fit electrodes to scalp. Oh, of course we have to have a scalp loaded to do that. This is not necessary, by the way, on the MR Viewer side, but we can see that what it does illustrate what just happened. The original ones were just a little bit off of the scalp, and we just fit them to the scalp. So I'm going to unload the scalp. If we want, we can now save this one. I just overwrote the existing one. Okay. All right, so all that was really not necessary for what I want to show you here. But as an aside, so I'm just rearranging this a little bit. Now I want to go to this mode here, warp to point. Now we can move around. Now here's cerebellum here. Okay, so now what I want to do is load this map data. So let's do this. Okay, now what it's showing us here first is the map. It'll be the average across the whole time period. But what we want, and I'll show you here, this one. Okay, warning, we're going to see a little bit of a bug here, but it's not going to be critical. And we're going to fix this. But let me show you what you need to do. If you don't do this, let me show you. If we go to Options, Display, Source Maps, this button is grayed out. In order to get this, we want to see the map as a function of time. So to do that, you have to double click here. Yes, you're going to get this message that can't be loaded. That's a bug that we'll fix. And then don't say remove the file, just say cancel. Okay, we're going to fix that bug, but the important thing is when you do that, now we do Options, Display, and Source Maps. Now this button is available, and that's what we want. So let's look here now. See, what it's showing us now is the average of all latencies from -300 to +300. But let's uncheck this. And now we can slide this around. And now we've got the map as a function of latency. And in particular, if we want, let's go back to EMSE Data Editor. When it's sort of at a maximum here, what that latency is if you look at the selection, it's at 87 milliseconds pre-event, so that's -87. It looks here like we've got some cerebellar activity here, which appears to be maximum on the left, but we also see it on the right. Let's go back to MR Viewer, and let's move to that latency, 87. There. Okay. So there's 87. And notice here, now of course this, as you know with EMSE, this is the radiological convention. So left shows on the right, and right shows on the left. This is from the perspective of the radiologist, not from the perspective of the subject. So here we are. Indeed, this is coming into cerebellum on the left side, but also we see some on the right side at this latency. And it's separated out, so this looks plausible because it's we have two hemispheres of the cerebellum, and we're seeing something in both. So that looks promising. And you can play with the whole. Now this looks interesting here. If we want to go up to that point here, this may or may not be, I'm not sure, but let's see what time this is. This is 141 milliseconds pre-stim. We can play with that a little bit. It's not necessarily the maximum, but I accidentally hit this one. It took me all the way to the end. Here we are again. So something in this time range, in about the -140 or so time range. Let's look at Data Editor. Maybe about here. Possibly. It's hard to tell which of these. There's some overlapping activity different oscillations that have a phase shift between them. But here at about minus 151, let's go to minus 151. That doesn't appear to be the max of what we're seeing in the source estimate. But this is of interest here. Possibly, I'll let Dr. Suzuki be the one to interpret it. But one possibility is it might be SMA, supplementary motor cortex. Possibly. It's on the midline. And it's known to be involved as a preparation to motor events. So that's a possibility. What I think might be going on down here is this may be picking up residual eye movement activity, which is well segregated, so I think we can ignore it. But it looks like it's locating pretty much to in the eye area. It's outside the brain. This, I can't tell you. It looks like it may be. It's basically picking up on the cerebellar activity that's bleeding over to the midline. So now we've got the whole time series. We can look at it before and after. Let's look after the movement. Yes, even that's before the movement still. So there are oscillations before the movement. We're still not at the movement yet. Now 8 milliseconds. Okay, they're right at the movement. We're not seeing anything at that moment. But after the movement, some cerebellar activity returns. Okay, so that's a first pass. And there are other things we can do. Now I want to return to this question of the reference. And we will need to discuss this, because the implicit reference seems to be doing a good job here. And by the way, how does EMSE handle the implicit reference? Well, EMSE is treating the implicit reference as if it were an infinity reference, an ideal infinity reference off to infinity. Obviously, the actual reference and recording wasn't, so we should probably find out what the actual reference is. You can tell me. But let me show you what happens when we change the reference to a common average. Now, here we are in the average. Let's go up here, and all these filters have been already applied. They're history filters. But now let's add the common average. We can do this because we're in the time domain, and that's allowable to apply the reference after the fact in the time domain. So I'll say, okay, now we have applied a common average reference to the data. And now I want to show you something that is legitimate, but you might think it's an error. If I go to display, refresh now, you'll see error. Inverse operator not valid for this filter pipeline. That message is correct. That's correct because we changed the reference, and the inverse operator depends on the reference. So that's correct. So let's close this out. Let's unload that Loreta, and let's just make a new Loreta inverse operator. And same as before, those are still set. The only difference being now that the reference is going to be with respect to a common average. Okay, this time I'm going to save the inverse operator, and I'm going to call this CAR for common average reference. Let's add that inverse operator. And now let's see. With the common average reference, we see that the nice cerebellar activity we saw at this latency here, now we don't see it. And so I do believe that the cerebellar activity we saw before is real. The common average reference is creating an issue for us. I mean, one reason, if we want to look at the we could, make map data and look at it in MR Viewer. But I already did that, and we can look at it at various places here to refresh. Let's just pick a few examples. Display, refresh. Now we are seeing a hint here of cerebellum at this latency with the common average reference. It doesn't seem to be lateralized though. Why might the common average reference be a problem here? One reason could be it's important to know that a common average reference is not the same for every recording. So if you have say a 256 channel recording, it's going to be the common average of all those channels. If you have a 128 channel recording, it's the common average of those channels. If we have a 64 channel recording, it's going to be the average of those channels, but it's also going to depend on what channels those are. So let's look here now at the scalp again and the sensors. The scalp, let's just make the content. Let's just let it be the wireframe so we can just look at the sensors. Okay, so there are the sensors. Now, because this montage, this electrode array was set up to emphasize the cerebellum region here. That means that this is going to be disproportionately represented in the average. And when we subtract out the average, we actually can be subtracting out the very thing we're interested in, which is the cerebellar activity. So so that's what I think is going on. And in addition, we have these two electrodes here down deep. That's good. In fact, if those are nice recordings there, we might want to use those as a reference. But they would also be picking up on some eye activity, these two as well. So to decide what to do with the reference. But I think this is explaining why when we use a common average reference, we're actually subtracting out, because of this, for the very reason that we made a dense, that you made a dense sampling back for cerebellum here, the common average is not the way to go. So that we could discuss that later. But for now, I think that it looks promising to me that at least with the implicit reference, we're getting two cerebellar hemispheres distinguished. That's plausible. And this looks like a good start to me. So with that, I will stop. And of course, there's plenty more that could be done later.